In a previous video, I created two particle systems, one in the shape of some text using the text to points method, the other without any shape and positioned away from the text shape system. When the programs run, the shapeless system moves toward and takes on the shape of the text. There's a lot you can do with this, so I wanted to explore it a little bit further. In that previous video, both arrays were of the same size, and the target array, the location that the shapeless system moves toward, changes while the shapeless points reset. I thought it'd be interesting to see what would happen if one line of text morphed into another, and this process would cycle through messages, maybe even display the date and time. So let's walk through this sketch and see what's going on. In our global space, we set up a few variables. We need one to hold our object that morphs the lines of text. We need an array to hold those lines of text. And because we're extracting points, vector locations from text that we give to this method, it needs font information. So we're going to upload a font into our sketch files, and then we're going to use that font in the parameters for the text to points, and I'll show you that here in just a moment. But to do all that, we're going to use a preload function and set the loaded font equal to that variable myFont. Then in setup, we're going to use the available window width and window height, and we're going to push into our messages array the list of texts that we're going to use. And you'll see here that there's commented out a string for clock and a string for date. Whenever the program reads a message that says clock or date, it's going to perform some separate action where it gets a formatted string for the date and a formatted string for the time. And then it returns that to the system, and then that gets displayed. But I've blocked that out for now because I thought it'd be a little bit distracting watching the clock go all over the place as I'm recording this video and editing it, and I didn't want that distraction. So I'll take that out later once I get to the end of the video, but for now I'm just leaving it the way that it is. Then we want to instantiate a new object of this morphing system. We're going to set that equal to the variable morpher, and then we'll make any changes to the graphics system that's going to run globally. So I wanted the stroke cap to be square. This is just an aesthetic thing. It's not necessary, but it's there if you wanted to change any of those attributes. That's where we would do it. Then we're going to refresh the background at least one time, a full refresh with whatever background color contrasts well with your output. Then in Draw, real simple, let's clear the background each frame with the color that's the contrasting color. And then we're going to execute the update function of the morpher object. Okay, let's look at this function. It has all the stuff going on. You can see it's pretty mighty. It's got a lot of stuff in there, but nothing that we can't figure out together. So let's look at this a little bit more closely. When we set up the initial state of our object, we need to assign some variables, set some values, so we're going to do that here. One of the first variables that we need is the size. When we get the points from text to points, when that array is established, those values, that size, is set with the parameter, which I just left it at 10. You can increase that to whatever size you need and just do it inside there. But I wanted to use a multiplier outside of that, and that's what this .size is doing. It's taking what is ostensibly a normalized value of points and expanding them times 8 here, or times whatever number you want, and that's going to increase the size of the output, the overall scale of the output. The next variable is speed, and this is related to linear interpolation. So the speed isn't a constant. It's actually starting out really fast and it's getting slower as it gets closer to the target position. So it's more of a rate of movement. And this is a value between 0 and 1, where 1 is really fast and close to 0 is really slow. So I wanted the text to be displayed long enough for you to read it. So I wanted the points to move slow enough for that to happen. So play around with that value so that it improves the readability of the output. Next is this close variable, or the closeness. So we need to reset the system. We need to switch from one text to another, or change the values in our target system. We need to know when to do that. So if we keep track of the last point in the system of moving points, When it gets so close to its target, then we know everything is in place, it's been there for a while, now we're ready to move to the next line. That threshold of 0.5, that's how close it needs to be to the target in order for this to happen. So that's what this is, just a threshold that switches text whenever the last point gets so close. Again, this is going to affect how long the output is going to stay before it switches. So playing around with that, you can get your timings adjusted. Whenever the system is reset, it needs to know what line of text it's on so that it knows which line of text to switch to. So we need a variable to keep track of that. And we're going to test that range to see, are we past the list of messages? If we are, then let's reset back to the beginning of the list. Next, for the style, the color style, we're using noise. And noise, a lot of times I'll just use frame count and multiply it times a coefficient to get the difference this moving wave action in the noise returns. But if you have a function that has a lot of processes in it, frame count isn't going to work quite right, because the way I understand it, the frame count is advanced every time the draw function is executed. So if you're doing a lot of processes that are cycling inside of a function, those processes are going to occur between frame counts. So if you're using the frame count to adjust any variable inside those cycles, it's not going to work right. One of the things that you can do is just fake a frame count and track how many cycles are going on inside your function that are different from the number of frames that are happening. And that's what I'm doing with this .offset. It's just going to be an incrementer of some decimal value that's going to act like the frame count times a coefficient that I can use in the parameters of noise to get this wave-like movement of color through my output. It's not necessary, it's just kind of there for the style. And I set it equal to a random number because I want a different value to start. I could make this an array and have each point be relational in its uniqueness and the way that the color moves through. That might be something later, but for now those are just, it's all kind of the same thing. So that's that. The next variable is the moving points. I call these darts because they're moving toward the target, like a dart moving towards a bullseye. And we're going to set that equal to a blank array, and then whatever points or whatever values we push into that array, they're going to start at the beginning, the 0 element, and move to the end of whatever the length of the array is. And then next I have time is and date is. So I have to format the raw time and date information into something we're used to seeing, and then send that string into the system so that it can have its points extracted, so on and so forth. So I need a variable, a function variable to hold that so that it can move between the methods in this function. Lastly, I set the size of the moving points array. I estimated about 550 points will cover each line of text pretty well. I'll play around with this. If you notice a lot of gaps in your output, increase this number. If you notice the performance is really slow, decrease this number until you get like the intersection of what looks nice. So we have our variables declared. Some of them are assigned, some of them are empty. We need to put some values in there. So let's set up our darts, our moving points. And we want the output to be centered in the canvas, vertically and horizontally centered. So we need to figure out some way of figuring out how to position these on the canvas so that they're centered. Or you might want to move them around the canvas randomly. If you do, you don't want them to be hanging off the canvas anywhere. You want them to be, the output to always be inside the canvas somewhere, right? So we need to figure out a width of that output. So figuring out the width of the output for the moving points is real easy, because when we create those, we're going to set those points equal to the center location of the canvas. So that's automatically done. They're all on top of one another, so the width of that array is just 1 point. But our target locations, that's going to describe some actual shape, and that's going to be a certain width and a certain height. The height is uniform because it's just one line of text, but the width will change depending on the line of text. So we need to be able to figure out what that width is. How do we do that? Well, when text to points gives us an array of values representing characters, those values usually go from an origin of 0, 0 to negative y values, that is going up, and to positive x values, that is going to the right. So if we go through the entire list of x values and we keep track of which x value is the highest or the rightmost location, then we know the width of that system. If it's normalized width, then we just multiply that normalized value and it gives us our scale value. So that's what we're going to do here. We need to keep track of a variable that will keep track of what the highest x is. We can do that with a local variable. And then we can use that to calculate the center position. Here we can see that there's really no calculation because the points in the darts are all on the same spot, so there's no width. But when we get to the target, then we have to start calculating things. So you can see here is a loop that goes through the entire length of the target array and figures out what's the rightmost x position, and then it has the width. And then once we have the width, we can go through that loop again and we can reposition all of those normal locations to where the center justified locations are. And that's what we do here. So the very first thing in this first loop, when we're trying to figure out how wide it is, we need to take the normalized size value here and multiply it times our scale value, the size. And then once it's expanded to the width that it's going to be as output, then we can know how wide it is relative to the output that's going to be displayed. If we don't do this first, then our width is only going to represent the normalized width, not the output width. So I run through the loop first, expand those points, find the widest or find the width point, and then run through the loop again and set everything to its center justified location. That's to start. Once we've done that, we have everything where it needs to be, we can set the system loose. Now we're ready to do the update method of our function. This is where everything is going to get animated, and we're going to do our test to see if things need to restart. So the very first thing that we need to do is the style component here. Let's just advance that by a decimal, and then we can use that in the noise later on and get our nice colorful output. Next, we want to loop through all of the dart particles, and the very first operation inside that loop is to find what our interpolated index value is going to be. So this I here represents the index value, a number for each element in the array, and we need this I to equal some value inside the target. So we're going to use map to do that. We're going to set the first parameter equal to what our object value is, and that's in a range from 0 to the length of the darts array minus 1. And then we're going to interpolate that to 0, from 0 to the length of the target array minus 1. And it's going to give us a floating point. If we set the return inside the floor method, that's going to return an integer, and then everything's going to be cool. So whenever we use I, the index value for the dart, we have to remember to use find I as the index value for the target in order for those two things to line up. So just keep that in your head for now. The next thing we want to do is test to see, are we off the first element in the array? If we are, then we know we have a previous element. So if I'm going to draw a line from the current element to the previous element, I use the current index value, make that point, and then draw a line from that point to the same point, except for the index value has minus 1. Well, if I'm on the first index value and I try to subtract 1 from it, there's no element there, so I'm going to get an error. So if we just check and make sure that we're not on the very first element, then we know that we always have a previous value to draw a line to. So that's what this condition is doing. It's making sure that we're not going to throw an error when we draw a line from the current point to the previous point. Once we've established that we're not on the first point, then we can start to draw our line. To draw our line, we want to do a couple things. First, we want to make sure if the line is short enough to draw. What does that mean? Well, all the points in the array are it's just like one system. Even though there's lots of letters in the system, that system doesn't know where one letter begins and where the other ends. So if you're drawing lines between all the points, you're going to join the letters with at least one line. How do we avoid this? We look at that line length. If it's too long, then we can assume that it's probably joining one letter to another, since all the points inside a letter are really close together. So if we just check for the line lengths that are short, we can assume that those points are close together, it's in the same letter, and we are safe to draw that point. So that's what this condition is doing right here. It's testing to see that it's within a certain range, and if it is, then we can draw that line. As for this here, it's basically finding the distance of the line from the current point to the previous point. If that distance is too big, don't draw a line. If it's short enough, draw a line. So that's kind of what's happening there. So we do some conditions for the output. Here is where I'm using the noise condition, and I'm using this.offset as a parameter. And then when certain conditions exist, it draws the output a little bit differently. I think in this case, it's making the bright little chunks that go around. Those are distributed through noise. That's why they kind of move through the system. So that's some of the stuff that you can do to stylize the output. But let's set that aside and let's just get to the meat potatoes. Once we've outputted a line, now we can move to the next position. And how do we do that? Well, we use the lerp method, and the parameters for the lerp method are going to be the object point is our moving point, and it's moving toward the target. We can see that here. So here's our moving point, here's our target point. Now what makes it distinct is we're comparing elements in the array based on the interpolated index value. So we have to be sure to put in I for the dart and find I for the target, and then those elements will line up. Otherwise, if you just put I here, you're going to run into an error. You're going to run out of points somewhere. If you put find I here, then you're not going to use enough points, or you're going to run out of points somewhere. So keep this distinct. And then for the rate of movement, or the interpolation difference, we're going to use this dot speed, and that's that decimal between 1 and 0. We're going to do this operation for the x and the y separately, and then we're going to test the distance that we get from that. This is going to let us look at the last particle and see if it's close enough to its target, and if it is, then we'll switch to the next text, and that's what happens here. It looks to see if it's on the last particle. If it is, it checks its closeness. If that's true, then it restarts the system. And by restarting, it just changes the target locations to the next text locations. What the hell is that? Oh, okay, yeah, all right. And then for just a little bit more stylization here outside of the loop, once all of the points have been drawn, I think, or no, this is inside the loop still. At random locations or random particles within the system, I draw some sparks, and that's what this is doing. It's just a spark animation. I can explain that to you, or you can look at it, figure it out, or just completely omit it. You don't even need it in here in order to see the output. Because well, that's pretty easy, how the system works, how the update is actually animating everything. So how do we reset stuff? Well, the first thing you want to do is blank out the target array. So we're going to push values into target. So we want to clear that array by setting it equal to a blank array. Now here's the thing with this. It's kind of redundant, because down here, this dot target is going to equal the return from text to points, and that's going to be an array from 0 to whatever the length of the number of points in that system. It doesn't matter if this dot target is a setup array already. It's just going to throw that out and put in new values. So it's kind of redundant to reset the system here, so I could probably comment this out and be all right. But I just wanted to put it in your mind that if you're pushing in values into an array and you want to start at the beginning, then just blank that array out, and that'll let you do that. The next thing we want to do is advance to the next message in the list. We want to test to see if it's if there's a message there, if we're at the end. If we are, then we'll just go back to the beginning of the list. Then this is where we look at the text, the string, and see if it says clock or date. And if it does, then we're going to perform the method that finds the string for that, and we're going to set that string equal to m. And then when we use text to points, we're going to use m as our text string. So if it's not clock or date, then m is just going to be whatever message is there. But if it is clock or date, we're going to change m from clock and date to the time and the day. And once we've done that, then we can go through the operation of finding out how to center our text. So we're just going to duplicate the same processes that we did when we set up the beginning conditions for this function. And once that's done, then we can return to the update method and continue as usual. And here real quickly is the clock method. We're just looking at the methods for getting the minute, time, and hour. I'm setting 0 equal to second, minute, and hour, because if you have if you're like on hour number 1, you're not going to get 0, 1. So your string would look nicer if it had 0, 1 in it or something like that. So I set everything equal to 0, and then if it is less than 10, then I'm just going to add the string. I'm just going to add those strings, and then I'll have 0 and whatever numbers there. Does that make sense? I do that for all of those, and then add AM, PM depending on whether or not whatever the meridian is. And then in the month, I just go from the string of array, this array of strings here, because the month returns a number. I want to associate it with the text, so that's how you do that. Then you give that formatted value to this variable. When you go back up into update, you can use that variable to set the message and then get the text to points out of it. So that's how that works. So I think that pretty much explains it all. If you have any questions, leave those in the comment. I'd be more than happy to clarify. If there's something that you want me to go over again, I would be happy to do that in the comments if I can briefly. If not, maybe it lets me know I need to do another tutorial. Let me know what you think of this. Give me a thumbs up, feed the algorithm. Subscribe if you haven't. If you have subscribed, thank you so much for the support. Hit the bell if you haven't, be notified for when a video is dropped. And I guess that's it for this one. Thank you so much for watching. I appreciate it as always. And until next time, take care.